Thank you very much. Most of the talks in this school were dealing with algebraic structures of quivers. What I'd like to present is some more geometry and to see how the different quivers arise they give rise to geometry, and they also show up in the physics of branes in space-time. So for those of you who were last week here, I talked about branes, and I had 3 types of branes, which we just called by a blue brane. We had a collection of them. We had green branes, which were intervals, and we had the red branes, which were looking like this. And based on such an arrangement of branes, we translated this to a quiver, where the number of branes, the green ones in each interval, K1, K2, K3, and so on, and the number of red branes will be N1, N2, N3, and so on. And so the resulting quiver would look like K1, K2, K3, N3, N2, and N1. Right? And so given an arrangement of branes, I can translate it to a particular set of integer numbers that are assigned in a quiver. The way those numbers are connected is given by the arrangement of branes. And now what we would like to do next is to try and compute the corresponding moduli space. And we call that the hyperkähler quotient, or Higgs branch. And we talked in detail about this construction in the previous 2 talks, so I will not do that. But instead, what we will do is to try and extend this picture to quivers which are kind of, they have some nice form of behavior. So the first thing I'd like to do is to put this direction here to be periodic. And if this is a periodic direction, then now those blue branes are placed on a circle, and the green branes are just stretching between them, like this. And so in the absence of red branes, then I'll get a quiver which from a finite A-type quiver now becomes a fine A-type quiver. So I could take the following picture: K1, K2, K3, and so on, Kn in a circular quiver. And so in such a way that now we are dealing with, we are wrapping a circle. In particular, if we pick the numbers to be 1, then now we get into the point of Klaim singularity. So imagine that I have n nodes. Yes? Yes, yes, yes. It's a necklace quiver. Thank you. So I have a necklace quiver with n nodes, and they are just connected along a circle. Every node has precisely 2 edges, and there is no orientation on those edges. And here, if we pick the node numbers to be 1, I get to the form of a Klaim singularity. And the Klaim singularity, there is a classification. Which goes by A, D, or E. And it's always of the form C2 mod gamma, where gamma is a discrete subgroup of SL2. Okay, so gamma is going to be, for the case of the abelian Orbifold, it's going to be gamma is equal to Zn. And then there is the non-abelian infinite sequence, where I use the dihedral group Dn. The order of Dn is typically 4 times n minus 2. And there are 3 exceptional cases which follow from the symmetry groups of the 5 Platonic solids in 3 space dimensions. And those are denoted by E6, E7, and E8. The groups are sometimes called the tetrahedron, which is self-dual. Then there is the cube. And the last one is called the icosahedron. Okay, and actually, all of these Kleinian singularities are classified by Dynkin diagrams. So the abelian one is the one that we just gave here, the cyclic. The dihedral looks like the affine Dynkin diagram of type D. 1, 1, 2, 2, 1, and 1, where the number of nodes here is n minus 3. And the 3 exceptional ones would correspond to the affine Dynkin diagrams of type E. 1, 2, 3, 2, and 1, 2, and 1. And then the E7 looks like this one, 4, 2, 3, 2, and 1, 3, 2, and 1. From which you can see that the orders of those groups, those finite discrete groups, would be here 24. Here it's going to be 60. And then for the E8 guy, it's going to be of order 120. And any questions so far? So given the prescription for the hyperkähler quotient that we gave in the previous 2 lectures, I can now compute the Higgs branch of those quivers, and I will find in each case that the moduli space is of this form, C2 mod gamma, where gamma is one of those discrete groups. Any questions about this? Yes. These numbers have both geometric interpretation and algebraic interpretation. So from the point of view of the algebraic interpretation, it's very simple. Every algebra has a highest root, and this highest root is written as a linear, positive linear combination of the simple roots, and the precise numbers would be those ones, right? So that's the algebraic interpretation. From the point of view of the geometric interpretation, these are the vector spaces I need to put in order to characterize to compute the singularity as a hyperkähler quotient, right? So remember that every edge gives rise to a cubic superpotential, two terms, one on each side of the edge. And I have also equivalence relations which act on left and the right of each edge. Right? Do I need to remind this? Or I just did it previously. So you just apply this procedure, look for invariants which satisfy the relations, and then you get this result. Let's do it for the case of the Zn. It's relatively simple. So first of all, let's remind what is C2 mod Zn. So I'm going to have the parameterization of C2 as two coordinates, Z1 and Z2. And the way the group acts on those two complex numbers is that they make an identification by a phase which acts with a plus sign on the first coordinate and minus sign on the second. Okay, where omega is just the nth root of 1. Okay, so this is the action of the discrete group Zn. And when I see, so what it means pictorially, we could think of this space. It's divided into n different wedges. And this identification tells me, this is in one of the coordinates, Z1, tells me that the point has n images. And all of these images are to be considered as a single point. That's the meaning of folding, right? It's called an orbifold because I take the real space and I fold it with an action which is an n-fold. Right? So I do this for the first coordinate, I do this for the second coordinate. And now, in order to characterize this space, what I do next is to look for invariants under this folding. So what kind of invariants do I have? Let's call the first invariant A, Z1 to the n is an invariant because omega to the n is 1. And also B, which is Z2 to the n, is an invariant. And C, which is Z1, Z2, is the third invariant. Okay? So this is geometrically the three types of invariants. And from those invariants, I can see that they satisfy the relation that A times B is equal to C to the n. So this is the algebraic variety, which is given by three coordinates which satisfy one relation. That's the embedding of C2 mod Zn into C3. Okay? Any questions? So C2 mod Zn is the set of three variables, A, B, and C, which satisfy these relations, this single relation. But I can ask, how do I get it from the quiver? Here's my quiver. And in this quiver, I have, remember that every edge gives rise to two arrows. Let's write it down. Let's call them A1, A2, A3, all the way up to AN. And the other one will be B1, B2, all the way up to Bn. And so from this, remember that every node acts with a complex rescaling, and that's giving me the equivalence relation. So if I take the product, over all A's going clockwise, I'll get a variable which I'll call A, not by accident. I match it to this. And then I can also take the product over all B's, call it B. And in each pair, A1, B1 equals to A2, Bn, and equals to A3, Bn minus 1, and so on. So from these, I recover this relation. Okay? So we did the C2 mod Zn singularity in two different ways now. The first one was to get it from the, that's just the way it's defined as an Orbifold. And the second is by computing the moduli space, so-called Higgs branch, the hyperkähler quotient of this quiver. I did it fast, so I skipped some of the steps. If you have any questions, please let me know. Yeah. Write bigger. Yes, that's a problem. Keep on reminding me. I'll forget, and then you'll just remind me again. Okay? More questions? Okay. So this constitutes the tiling of a circle, right? So I'm going to think of this system as tiling a circle, dividing it by those blue branes, as many as the order of the singularity, and just putting one brane in each of these places. And the next thing, which is very natural from the point of view of string theory, is to extend this tiling from one-dimensional tiling with a one-dimensional interval to tiling of a two-dimensional torus with two-dimensional objects. And that's what we're going to do now, two-dimensional tilings. Right, so I'm going to make a switch from the topic of the previous two lectures where we were doing one-dimensional intervals. We got this set of quivers. The particular sub-quiver, very special case, is this one. And I'm going to take this one-dimensional tiling and extend it into a two-dimensional tiling. Any questions? Yes. Those what? I cannot hear. the capital A and capital B. So we say that for every edge in this, 2 lectures ago, we called this a graph. For each such graph, we make every edge will now become bidirectional, 2 arrows. And what we do is we think of the A1 and B1, we think of them as if the node numbers are K1 and K2, we think of them as rectangular matrices, K1 by K2 or K2 by K1. But for the special case where both of them are equal to 1, then each of these objects is just a complex number. Right? So it's a complex variable. So I have 2n complex numbers over here, which carry different. This is what we call charges, right? So when I have the equivalence relation, it tells me that I take G1 in GL K1 and G2 in GL K2, and I say that A1, which is it is going from K2 to K1, so it has dimensions K2 by K1, right? And it is the same as G2 A1 G1 inverse. That's the equivalence relation. So I'm looking for the set of all matrices A and B which are satisfying such an equivalence relation. And if K1 and K2 are equal to 1, these are just complex phases that I multiply. There's no notion of left and right here, but it's just complex phases. And I'm looking for all of the invariants that under such rescalings, subject to the relations which come from the superpotential that we wrote in the previous 2 lectures. So I just skipped these points because we wrote them in the previous 2 lectures. So as an exercise, convince yourself that what I did here very quickly is the correct answer. Yes? I don't assume any commutativity relations, no. I just think of them as matrices. More generally, I should think of them as just algebraic objects in some abstract algebra, not matrices. For the physics application, it's enough to think of A and B as just rectangular matrices, and naturally there's no commutativity there. So I have to be careful about the order of A and B. But more generally, I just should think of it as just abstract objects in an algebra with relations. So, yes, so I suspect that in the context of cluster algebras, this coincides with the notion of pre-projective algebra. So you are familiar with this, but possibly with a different name. So I think if we will check enough, we will find that pre-projective algebras are the same as Higgs branches, what we call Higgs branches in physics. but let's check this. Okay, so but we did this thing, and the point is that using such quivers, I get a two complex dimensional singularity. And this is the line of thinking that I want to take. I want to extend the singularity to three-dimensional and the tiling from one-dimensional to two-dimensional. And this is the thing which naturally arises in the string theory setting. So that's why I want to get to two-dimensional tilings. And the simplest quiver that we will take now is the quiver with the three loops. This is the clover quiver. And there is a dimension vector here. Well, just one. Let's call it K. So a single node with three loops. And a superpotential. Which is a cyclic superpotential. So whenever I write a monomial, it should be understood as a cyclic combination of the variables. So if these were matrices, I would just put a trace. So ABC minus CBA. Okay, so I call each one of these loops A, B, and C. So I have three arrows, one node of rank K, and I'd like to compute the moduli space of this quiver. Any questions? So, again, the equivalence relation will tell me that because this is an arrow which starts and ends at the same node, I mean, here perhaps I should put some physics terminology. This equivalence relation that we are using is called in the physics literature gauge invariance. Okay, so the equivalence relations will tell me that there is an element G in SL GLK, and each one of these guys is the same as G A G minus 1. Okay. Furthermore, there are, since there is a superpotential, we are going to look at the critical points of this superpotential and to get some relations. And the relations would be just commutators in this particular case. So if I differentiate with respect to C, I'll get AB equals to BA. If I differentiate with respect to B, I'll get CA equals to AC, and if I differentiate with respect to A, I'll get CB equals to BC. Three equivalence relations, which tell me that those matrices commute, and therefore it's enough to, because of the equivalence relation with the GLK here, it's enough to, I can pick those G's such that they will form diagonal matrices, right? So the parameterization of this space would be most convenient by using the eigenvalues of those matrices A, B, and C, right? So I have K eigenvalues. Which are parameterizing C3K. However, I have a freedom to rearrange those, since I'm dealing with a k by k matrix, I have a freedom of rearranging those k in a particular permutation. I can put them anywhere that I want, and so there is a natural action of Sk. Sk is the permutation in k elements. Was this too quick? Oh, this is good. So the moduli space is the kth symmetric product of C3. Sim K. Yes? Those are the critical points of the superpotential, right? So whenever we do this notion of quotient, we have two steps. One are the equivalence relations, the gauge invariants, which are just acting on the matrices from left and right. So typically, those two elements will be different. One at the start and the other at the end, but here, because it's a loop, it's the same element. So this is the equivalence relation. The second is the relations that I get from a superpotential. So I write a superpotential, I compute all of the critical points of this superpotential, and I impose these as additional conditions. So if instead W would be 0, I won't get those commuting relations, and then the moduli space will be much more difficult, very wild in behavior. The dimension will go like k squared, whereas here the dimension, it's a very tame moduli space. It has only dimension which is linear in k. So a proper choice of the superpotential, which from the physical picture is done very carefully, and I'll show how we do that, would give me a moduli space which is linear in k and also contains the number 3, right? So the dimension of this space here is 3k. 3 comes from the fact that I have 3 arrows, and k from the fact that I have k identical objects. So let me now present a physical picture, and which will help in understanding why we expect the moduli space to be the symmetric product of C3. Right? So the stringy embedding is, we are taking, so recall that string theory is a 10-dimensional and 9 space one time. What we are doing is to take R1, 9, so 1 time 9 space, and we are going to break it to R13 times space that we will call X. And this X is going to be of the form of a singularity. And we're going to take this singularity to be of the type Gorenstein. And soon I'll give you examples. To get the precise definition of Gorenstein, we will have to take through some steps. But in the talks that we had yesterday, there was a mention of the notion of a 2 Calabi-Yau and a 3 Calabi-Yau. And so a Gorenstein singularity, in a simplest possible way, should be thought of a singularity of a complex 3-dimensional Calabi-Yau space. So this is 6 real dimensional, and we are going to take it to be a complex manifold and of type Gorenstein singularity. Well, the simplest possible choice that we can do is to say that is just flat. Just C3, and indeed, if I take, I go back to this quiver, I put the number k equals 1, the moduli space that I get is C3. So, so here's the picture. Let's draw the space X here, and this we are going to take these as points. We're not going to draw anything about R13. And so if I place, so I'm going to place a brane. It's called the 3 brane on R13. So it fills this space, but it's point-like in this direction. So when I draw, it's just going to be a point. And I have k of them. So if I have k of them, I'll just draw k points, k identical objects. And from this description, it's very natural to have an SK symmetry, because those are identical objects. If I'll exchange them, permute any of them, then I'll get the same picture. So there's not natural action SK, and each point can be anywhere on C3, and therefore the moduli space of a single guy is going to be C3 for k equals 1. If it's more than 1, then I'll have k points on C3, and I'll just take the symmetric product of them. Okay? So again, we got that the moduli space is the symmetric product of k points on C3. Okay? So I had 2 derivations here. One derivation is by applying the physical picture of k points in C3, and the second is by explicitly computing the moduli space. Sorry. This is what we would expect from the generic picture. If for a space X, or for a singularity, the moduli space is the symmetric product of X, which is X to the K divided by Sk. Okay? So we are going to now apply the intuition that we said here. Not just take X to be C3, but to take it any Gorenstein singularity, and the moduli space is going to be this one. And the next step will be to construct the quivers such that their moduli spaces are of the form of symmetric K of X. Any questions? Is it too fast? Yes? 3-dimensional, yes? It has dimension 3 times k, not too large. I mean, it's just linear in k. Yeah. So imagine that I take three branes which fill R13, and they are point-like in the remaining 6 directions. So it could be anywhere. It could be at the origin, it could be away from the origin. It's just going to parameterize a point on X. Each such guy. So I have K objects. Each one is a point on X. Right? And so because those are three branes which are just identical objects, I expect that the moduli space will be symmetric product of K points on X. That's the very, very naive physical intuition. Without doing any computation. The nice thing about physics is that when you have the right picture to understand a particular system, you also have some intuition, which gives you a prediction, and then you could worry about the details of how you get it from a mathematical formulation. So that's the thing that we have over here. We have K points on X, and therefore we should expect this moduli space. More points, more questions. So let's take the next singularity to be of the form of C3 Z3. So this is, if you want, this is a non-trivial Gorenstein singularity. And the Z3 acts by taking three coordinates, Z1, Z2, and Z3, and identifying them with just a phase, omega Z1, omega Z2, and omega Z3, such that omega is equal to 1. Okay? So this is the space C3 mod Z3, and my goal is to compute a quiver such that the moduli space of this quiver is going to be C3 mod Z3 for the case k equals 1, when I take one such brane, and it's going to be the symmetric product of C3 mod Z3 when I take more than 1. Yes? The origin in this case is conical. Looks like a cone here. Where that's the only singularity on this space. Any other point away from the origin is a non-singular point. Right? Over here, you could look at this equation. This is a homogeneous equation. Therefore, the only singular point is the origin. Right? And it's conical. Every solution of this, if I rescale it, will also be a solution. Okay? Just because these are homogeneous equations. And so this is the way we should think, right? So more, if I go back to this picture where I have a 10-dimensional space-time, 6 of them are going to form a singularity. There's going to be a special point at the origin, which is the tip of a cone. And then there is going to be a 3-brane, which is just placed at the tip of this cone, and we are going to ignore the 3 plus 1 dimensions here. They're not going to play any role. Instead, we are going to look at the behavior of this system in the 6-dimensional transfer space, which is a singular space. Okay? Yes? Questions? Okay, so how do I go and solve such a system? Let's first of all compute invariants. How many invariants do you expect in this particular case? Do you know? So here's a point with the nice representation theory. because the action, the Z3 action on those three coordinates is the same action. So there is an SL3 which commutes with Z3 inside, well, it should be GL3. Let's just take it to be GL3. GL3 would just rotate the coordinates among themselves, and there is a discrete group which acts on those three coordinates. So GL3 divides into C star times SL3. The C star is not commuting with Z3, but SL3 does. Okay? And therefore, I should use a representation theory of SL3. So for example, those coordinates Z1, Z2, and Z3 transform in the three-dimensional representation of SL3. But I'm looking for invariants. So can I construct invariants? At linear order, there are no invariants because they are, the coordinates are mapped to themselves by a phase. So I lost the invariants. At quadratic order, I can take a product, but again, it's going to transform. The first invariant that I will have is cubic. And it's going to be Zi, Zj, and Zk, where I, J, and K can be either 1, 2, or 3. Right? Any choice of I, J, and K, for example, if all of them are 1, Z1 cubed is an invariant. Now, if one of them is 2, Z1 squared times Z2 is again an invariant. Altogether, how many invariants do I have? 10 invariants. Right? This is the third-rank symmetric representation of SL3. Of the C3. So this is the representation with highest weight. Uh, 3, 0 of SL3. Is this notation acceptable, familiar? Is it okay? Right, there are two fundamental weights of SL3, and this is the notation for the highest weight, which takes 3 copies of the first fundamental weight and 0 of the second. Okay? Very good. So I have 10 invariants on this space. This space is generated by 10 invariants. And they satisfy some relations. To compute the relations, I'll have to work a little bit harder, but it's not so bad. I'll just need to compute that the second symmetric product of this representation is going to give me the representation with highest weight 6 and 0, and the representation with highest weight 2, 2. This one has dimension 27, and this one has dimension 28. Right? So when I symmetrize a 10-dimensional representation, I get 55, and those divide into the 28-dimensional representation and 27-dimensional representation. Okay, so just a simple lead theoretic computation, and it tells me that those are going to be the relations. So the space is going to be given by 10 variables which satisfy 27 relations. Complex variables satisfying 27 relations. These 10 variables transform in the representation 3, 0, and the relations transform in the representation 2, 2. Any questions? The 6, 0 are going to be invariant coordinates, so I'm not going to set them to 0. The 27 don't show up as variables on C3 mod Z3, and therefore I just need to set them to 0. Yeah. Yes. How do I compute that there are exactly 27 relations? So there are, so on C3, here we could do some, we could draw some lattices. It's a whole thing by itself. I was trying to be quick about it, but if you look at the set of coordinates on C3, you could draw the three-dimensional space and consider this as lattice, a three-dimensional lattice, where this is the point which characterizes all of the holomorphic functions of C3, which are constant. So that's the origin. The first point here will be a holomorphic function which looks like Z1, Z1 squared, and so on. Here, Z2, Z2 squared, Z2 cubed, and Z3, Z3 squared, Z3 cubed. So there is a three-dimensional lattice, the positive octant, and every point in this positive octant is going to represent a holomorphic function on C3. Now we can just do projections and see that these three form the three-dimensional representation of SL3. If you look at this slice here, you'll find another triangle. Now you'll find 6 points, and one which is above. 6 points which transform in the second symmetric product of SL3. And each time you go one step higher, you'll go up in the degree of symmetric product of those functions. Now, this is on C3. What happens when we divide by Z3? It tells us that only triangles which are mod 3 will survive. Right? I remove 2 out of 3 triangles, I remove 2. I'm only left with those triangles which are 0 mod 3. Okay? So if I'll just compute number of points, I mean, that's a simple computation. The total number of points on this interval is going to look like 1 minus t cubed Right, so I'll expand like that, and this is going to be the number of points in the triangle endpoints away from the origin. So you see that if I take n equals 1, I'll have 3 points. If I'll take n equals 2, I'll have 4 choose 2, which is 6 points, and then the 10 points will be for 3. I'll have 5 choose 2, which is 10, right? And when I impose the Z3 relation, this is going to turn into mod 3. These are all of the points on C3 mod Z3. I just removed all of those ends which are not 0 mod 3. So the first guy will be 10. One after that is 28. 6, 0. You see 6 is divisible by 3. That's the first number which is divisible by 3 after 3. Everything else must be a relation because it doesn't show up as and so here it's just straightforward. When I symmetrize 10 objects, I get 55. 28 of them are valid. Then the remaining will be relations. There's not more, not less. Precisely 27. There's no negotiation here. All the cubic relations will be result of the quadratic relations. Just multiply, and you'll get, those are known as syzygies, if you're familiar with the topic of syzygies. Here again, I'm trying to be as quick as can be. We could go into the details, and I'll be happy to go into the details. My goal is to show the general picture of what we are doing with geometric singularities. And we want to extract the quiver. Right? We want to get a quiver. Once I have the quiver, I'll be able to do mutations on this quiver, and then we can relate to the topic of this school. Okay? So that's my goal. Given a geometric singularity, I want a prescription that will give me a way to draw a quiver. Once I have this quiver, I can play with all of the algebraic games that we see here in other lectures. So how do we do this? So that's the next step. Since we are dealing here with an orbifold, we need to understand the different irreducible representations of Z3. This is a cyclic group, therefore every representation is one-dimensional, and they are just characterized by phases. Right? So there are 3 irreducible representations, 0, 1, and 2. And if I look at the way the embedding goes, I have that the 3-dimensional representation of SL3 divides into 3 one-dimensional representations of Z3. So I can write it as 3 goes to 1, 0, plus 1, 1, plus 1, 2. The 3-dimensional representation of SL3 divides into the 3 irreducible representation, the trivial, the multiplication by a phase, and by its inverse. Now I'm ready to draw the quiver. the quiver is going to have as many nodes as the, as many nodes as the number of irreducible representations. Let me write, I accidentally erased this. And what I'm going to do is to have 3 nodes, which will be denoted by 0, 1, and 2. So each node corresponds to the irreducible representation of Z3. And I'm going to have arrows which will tell me how the wait, I'm sorry. No, actually, I don't want this. There is such an embedding, but this is the wrong embedding. Sorry for that. It should have been this. What I read from this embedding here. Here, you see? So the first coordinate is shifted by a phase, the second by the same phase, and the third by the same phase. So the 3-dimensional representation decomposes to 3 copies of the same representation. So what I have is a combination. So I look at this decomposition, and I say that if I start with the trivial representation, there will be 3 ways of getting into one-dimensional, into the irreducible representation 1. So I'm going to draw 3 arrows here. And 3 arrows here, and 3 arrows here. Let's call those arrows by AI, BI, and CI. The superpotential, first of all, I'm going to arrange those into a 3-by-3 matrix. A1. And C1. Let's call it M. Okay. Yes. It's just that it's not so crucial. It's given by this choice here. More generally, I'll have Zn is generated by a single generator, and I just need to determine the power of this generator. Yeah, so I could have chosen -1, -1, and -1. It's completely equivalent, and then I would just reverse the orientation. And I would get an equivalent quiver. Yes? Exactly. Very good. Thank you. So this quiver is nothing but the tensor product of the 3-dimensional representation with each irreducible representation. That's the generalization of a Amihay quiver into 3 dimensions. There are some issues with this, but so far we didn't encounter them. And there's going to be a superpotential, which here takes a very nice form. That's the only superpotential which is invariant under SL3, and it just gives it uniquely, right? So it's just the determinant. In principle, I have 27 loops in this quiver, 3 from here, 3 from here, and 3 from here. So altogether, 27 closed loops. However, only 6 out of 27 are going to enter into the superpotential. And the way they do it is in a way which is invariant under SL3, and there's only one invariant I can write down. So here I could determine the superpotential in a unique way, but I'm not satisfied with this description because there were many steps I skipped while deriving this. What I want to do is to give a prescription which is generic for any Orbifold. Any questions? However, at this point, what we can do is compute the moduli space. What does this relation tell me? Tells me that AI Bj is equal to Aj Bi. And the same for C and BC. Right? I mean, just compute. So, or in other words, the indices on those A, B, and C commute. I can take the indices and commute them at will, and I will still have the same invariant. So now, let's write down the invariants. So I have 27 invariants, as we said, AI, Bj, Ck. Each one of them runs over 1, 2, 3. So 27 invariants. However, there are the relations which tell me that all of those indices commute. So only 10 out of 27. Right? Is this clear? So now I recovered my result from the description of the Orbifold. Right? So the first thing I did was to take the Orbifold, define it as a quotient by a discrete group, and found that there are 10 invariants. Next thing I did was to draw a quiver with a superpotential. Here's the quiver, here's the superpotential. I derive the invariants and I find the same 10 that we had over there, provided that the node numbers are 1, 1, and 1. So here's my quiver. Three here, and 3 here. Superpotential is that M. If you'll compute the moduli space of this quiver with this superpotential, you'll find that it's equal to C3 mod C3. Okay, so I invite you as an exercise, convince yourself that this is the moduli space. If you have a problem in showing this, please let me know, we'll go over the details. Show that given this quiver and this superpotential, where the node numbers are 1, well, be careful, because in this quiver, I denoted each node of the quiver by an irreducible representation of Z3. In this quiver, I denote each node by the dimension vector. So now take this quiver with this superpotential and use the rules for computing superpotential, for computing the moduli space, namely, use the equivalence relations together with the relations that you find from the superpotential and show that the moduli space is C3 mod Z3. Meaning 10 variables subject to 27 quadratic relations. Okay? Any questions? I'm being too quick. I feel that I'm doing it too quick. So please stop me with questions. No, no. No, no. Let me be explicit. So you see, when I compute the determinant, I will get 6 different contributions. The first one of them will be A1, B2, C3. A1, B2, C3. And then every permutation of this with signs will give me the other 5. So the next one will be minus A2. The order of A will, ABC still remains the same. A2, B1, C3. So what it means is that I take the 2, the second A from here, the first B, and the third C. Right? Those numbers will always be 1, 2, 3, but with a permuted order, and the ABC will remain the same. Okay? Plus permutations up to signs. Now the equations, C3 appears twice here, and so I get the relation A1, B2 is equal to A2, B1. Meaning when I write such an invariant, the ABC remain in the same place, but the indices can be freely changed because of such a relation. That's why I get, instead of 27 relations, 27 invariants, I only get 10 of them because the others are equal to each other by these relations. So it's the third rank symmetric representation of SL3, just like we computed it from the description of the Orbifold. And so it's a fun exercise, and also it's a nice exercise with the representation theory of SL3. And so I encourage you to do that. And if you really want to see the details, I mean, we could put many details. It will just take time. But we could really work out all of the details. It's a very nice exercise. More questions? So now let's give a prescription. Remember, my motivation came from the desire to make a two-dimensional tiling from the one-dimensional tiling that was erased over here. I want to turn this quiver into a two-dimensional tiling. And then we will see connections to the talks that you heard a few days ago. So here's the point. I'm going to generalize my Orbifold from Z3 to Zn, any n. And I'm going to put, so there are n irreducible representations. And Z1, Z2, and Z3, in the most general case, will be equivalent to omega to the power A1 times Z1. So I rotate it by a phase, which is the power A1 of the generator of Zn, A2, Z2, and A3, Z3. There's one restriction. We need to finish, so let me just give the description, and then we will finish this. There's one restriction. If you noted, the product of phases here, this phase times this phase is 1. And over here, the product of the three phases, this times this times this, is also 1. This is going to be a restriction. And so the restriction is going to be such that A1 plus A2 plus A3 is equal to 0 mod n. Okay? Why is that? It's because we want to embed the discrete group Zn into SL3 rather than GL3. Namely, we want that the determinant is going to be 1 rather than a generic phase. That's, sometimes this is called the Calabi-Yau condition, or the condition for being Gorenstein's singularity. And so my three-dimensional representation is going to decompose into three one-dimensional representation, 1A1 plus 1A2 plus 1A3, and correspondingly the quiver will consist of n nodes, and each node will have 3 arrows, which will be, if this is node I, then first arrow will be I plus A1, then the second will be I plus A2, and the third will be I plus A3. So now imagine a quiver with n nodes and 3n arrows, and the 3n arrows are precisely in this orientation, right? I just add A1 to the label of the node, A1, A2, A3 to the labels of the node, and I get the quiver. So for example, Z5 with the action 1, 1, and 3. The quiver is going to have 5 nodes. Two arrows from every irreducible representation, corresponding to those two ones. And the third one is going to jump by 3. From here, 1, 2, 3. So I'll get this. Okay. It's a magic triangle. It's a black magic pentagon. Huh? Okay. So we understand how to draw the quiver. We don't have time, so in the next lecture I'll describe how to get this quiver and the superpotential from a tiling problem. Thank you.
Thank you, Amihay. Any questions?
How do I construct the quiver? So, this I picked an orbifold, Z5. So now my orbifold is going to be C3 mod Z5, where I act on the 3 coordinates by omega Z1. Let me write it down. So Z1, Z2, and Z3 are identified with the phase omegas times Z1 for the first coordinate, omega times Z2 for the second coordinate, and omega cubed times Z3 for the third coordinate. So this is my identification. And, you know, it's actually a nice problem to ask how many different orbifolds do I have. If I fix the order of the orbifold. There are several ways of acting, and some of them will give equivalent geometric spaces. Some of them will be different, and so you want to ask how many different orbifolds there are. And the solution to this problem involves multiplicative functions. There is there is a function which is called the sum of divisors. It's a number theoretic function, and it turns out that it gives the solution to this problem. Now, but Z5 has only one possible orbifold, which is of this type. And so, as a geometric space, here's the space. Here's the definition of the space. I take C3, I identify the points by these identifications. The next thing I want to ask is to construct a quiver. How do I construct a quiver? I use this idea that I take the three-dimensional representation of SL3 and divide it into the one-dimensional representation of Z5. And so this gives me the composition. So the three-dimensional representation of SL3 divides into the first non-trivial first and the third non-trivial of SL4. So of Z5. Right? So the 3 of SL3 divides into 1, 1, and 3 of Z5. And the next point is that I draw the quiver, which consists of nodes, as many nodes as the number of irreducible representations. And from every irreducible representation, I just characterize the way those irreducible representations make tensor products with this three-dimensional representation, 1, 1, 3. So I take two arrows from one representation to the next. Right? So if this is the representation 0, then I move twice to representation 1, and I move once to the representation 3 here. So I jump 1 and 1, 2, 3. So I get a quiver where every node has 3 incoming arrows and 3 outgoing arrows. So altogether, there are 5 nodes and 15 arrows. However, this gives me the quiver itself. It doesn't give me the superpotential. I'll have to make a prescription for the superpotential. And for this, the best way to do it is to draw a two-dimensional tiling, which we will do in the next. We'll play with hexagons. Tiling hexagons. Tiling tori with hexagons. And then it's going to be related to the material that Jacob showed us. Very nice construction, actually.
Any more questions?
Yes. We could by introducing parameters which are associated with the nodes. I typically don't study this question, but many geometers do study the. It's certainly an interesting physical question. It's just that I don't I typically look only at the singular space. And in terms of the quiver data, so maybe you're familiar with the notion of a moment map. Every node has a moment map. Not so familiar. So the thing is that you have 5 nodes here, And for every node, you could introduce a parameter such that an overall parameter will be redundant. So altogether, I have a 4-parameter space here of deformations, and those will give me the different possible resolutions of this space. So I'm going to write down I'm going to modify equations. So in equations that I wrote down, all my equations were homogeneous. When I wrote down the relation AB equals C to the n, this is homogeneous. But I can make it non-homogeneous by making it look like product I from y1 to n, C minus, let's pick coordinates xi. Okay, so what I did was to take the monomial c to the n and deform it by lower monomials. Right? Instead of a polynomial of order n, it's just all lower monomials in C, and the interpretation of those x's are the sizes of P1s. So if you're familiar with the geometry of C2 mod Zn, it's a two-dimensional space where n-1 P1s have vanishing size. Right, so the second homology of C2 mod Zn is n-1 dimensional, and so I can pick a basis and resolve sizes for n-1 P1s. And the x's here would be the parameters would be related to the volumes of those P1s. So if all of them are 0, I'm at the singular point where all P1s have 0 size. If some of them are non-zero, then some P1s have a non-zero size, and I can just do the game as I want. Right? Now, in terms of the quiver data, those xi's would show up as parameters which are introduced on the necklace quiver. So I have n nodes. There's one node which is redundant. There is a sister action which is redundant, and so I have altogether n-1 non-trivial actions corresponding to the n-1 different resolutions that I have over here. So there's a very nice match between the number of parameters I can introduce in the quiver and the number of resolutions that I can put over here. And so I can do this game. This will change the equations. So it will end up looking like this. Also in the, I'll have to modify those equivalence restrictions slightly in order to accommodate for the those extra coordinates. And this has been done. People play with it. I find it less interesting problem, therefore I don't do it. However, I'm not. There is a guy called Fayet, a French physicist. So those resolution parameters in physics are called Fayet-Iliopoulos terms. You may know Iliopoulos is one of the great French physicists. So yeah, so in physics certainly they play a very important role, so important that they were given names of two people.
Thank you, Amihay.
Thank you.